In this video, we're going to introduce the concept of the electric force. It's going to build upon the ideas that we've experienced with the electric field. To that end, we're going to go ahead and start off with a positively charged particle right here. And that positively charged particle is just going to have a Q of 3 nanocoulombs. And I want to find the field at a distance. I'm going to go with r equals 5 centimeters away. So somewhere over here is 5 centimeters away. And I want to know what is E at that location. So that's what I'm interested in. I'm just going to kind of minimize that. Move it over here so we can reference it as we do the math. And I'll go ahead and write that out. E is KQ over R squared. And if we plug that in, let me grab my calculator. Very good. I'm getting roughly 10,800 newtons per coulomb. And again, I just want to kind of shrink that down. That tells me what E is. And now we're going to talk about the electric force and how it relates to what we've just accomplished right up here. So, what we want to look at then is the electric force. Kind of as an analog, we can talk about gravitational force. Here in our planet, Earth, a particle near Earth experiences an inward force that we refer to as down wherever we're standing on the Earth's surface. This inward force towards the center. That force is related to this gravitational constant. Don't call it the acceleration due to gravity, even though the units are of acceleration, newtons per kilogram. That's more of actually a gravitational field. And it's a product of that G value, which is universally 9.81 newtons per kilogram. It is a product of that G value and the object's mass. You normally see this written the other way, and that's the force of gravity. You normally see it written as mg. Now, wouldn't it be something if the force that a particle experienced related in the same way electrically, with like an electrical force? Well, it turns out that that is indeed what happens. So we'll just kind of box that off there, and we'll go back to our picture over here. Well, not that. There we go. Move that back up. We'll go back to this picture here, and we're going to ask not just what is the field there, but we're going to put another positive particle there. I'm going to overwrite it and say that it has a Q of 4 nanocoulombs. And I want to know what force does it experience. And remember how I said that wouldn't it be nice if we could relate it back to this relationship? And I told you we could. Sure enough, the relationship we're going to be looking at looks like this. The electric force is equal to Q times E, where E is the field that we just found. So the only step we need to make now to go from where we were with the electric field is multiply it by this new value Q to determine the electric force that that particle would experience. So let's go ahead and do that. I'll grab my calculator and we'll calculate the electric force. The electric force is going to be, it's going to be 43.2 micronewtons. That's 10 to the negative 6 newtons for everybody playing along at home there. So 43.2 micronewtons is the force that experiences. And of course, this all relates back to Newton's second law. If we were to do a sum of forces acting on this, gravitationally speaking, this 4 nanocoulomb charge probably doesn't have that large of a mass, so we can say that the gravitational forces on it are negligible. It's going to be this electric force, and then that will equal the mass times the acceleration of the object. So if we knew the mass of this 4 nanocoulomb object, we could then calculate the acceleration, and the acceleration would probably be very large for such a small mass that it would most likely be, being a 4 nanocoulomb charge. But it would probably give us a huge acceleration, even though our force isn't that large. So that's really all there is to it. The only step beyond calculating the electric force from the electric field is just this little extra piece where you're multiplying Q times E, which you already know how to find from our previous sections. So that's going to conclude our first video dealing with electric force. We may do a couple others as time goes on, but it's a pretty simple concept once you got fields down. That's why we did it first. For you to try at home then, I just want you to do two things we're going to change up. I'm going to show you in white. One, we're going to treat this new problem as the same source charge, so Q1 and Q2. Q1 is going to have the same source charge of 3 nanocoulombs, but Q2 is going to be negative 5 nanocoulombs, and the distance between them, R, will make 3 millimeters. I'll squeeze that in there, millimeters. So 3 millimeters between them. So we brought them closer together, and you'll notice that they have opposite charges. So I'll let you kind of puzzle out what is going to happen as a result of that. And you can come to class and we'll talk about it there.